in fact, let me even start with a small plan for this first session. We're going to have a talk for 50 minutes and then a 10-minute break from 3:50 BST, so British summertime, to 4 p.m. British summertime, followed by another talk. And then at 4:50, there will be a longer break, 4:50 British summertime. And on that, I am very pleased to introduce our first speaker. Our first speaker, University of Oxford. She researches fundamental issues in physics. In particular, in a recent research, she's worked on a new fundamental theory of physics called Constructor Theory, which is a generalization of quantum information theory. I should also mention that she recently published a good book about it. If people are interested to know more, I think it's called The Physics of Can and Can't. On that, Chiara, please have the floor, and please correct me if I misintroduced your book.
No, that's great. Thanks. Thanks, Charles, for this. Thank you and Sam for organizing the conference. So I'm kind of very, very happy to be able to speak at this conference. It's very nice. I think my talk will be exploring things that are in a way related to Everettian quantum theory, but we'll try to go beyond it in some way. And I'm hoping to keep this open so that we can have a nice conversation. Maybe some things I would say are slightly controversial, so I'm very happy to have a good discussion going. And so interrupt me at any point if you want to have clarifications or anything as I'm going along, because it's a very informal presentation. That's why I called it Musings on the Universality of the Quantum Multiverse. So the starting point will be this particular thing in Everett's work that I find very interesting, and that's one of the aspects of the particular way that Everettian the quantum theory, the Everettian take on quantum theory has to look at quantum physics, which hooked me, and it's the thing that I like the most. And it's the fact that Everett was seeking unifications. So this is evident in many parts of his thesis, but I think, for example, this nice sentence could be like a nice starting point, where he says that his thesis is devoted to showing that the concept of a universal wave mechanics, together with the necessary correlation machinery for its interpretation, forms a logically self-consistent description of a universe in which several observers are at work. And with this starting point, and with the work of many people, including many of the people who are today at this conference, I think it's very beautiful that there is one way of looking at quantum theory that allows us to consider it as a universal theory in a consistent way. Now, just a disclaimer, what I'm going to say from now on, with the thing I'm going to call quantum theory, is unitary quantum theory understood through the Everett interpretation. So I won't sort of all the time say unitary quantum theory, but that's what I mean. And I also intend it not just as an assignment of a wave function to the universe, but I also regard it as the set of formal and informal statements with which you specify things like interactions between subsystems, so Hamiltonians or Lagrangians or whatever. And this is in connection to the discussion we had yesterday. I think quantum theory means exactly that. So not just states, but also interactions and dynamical laws and so on. Okay, so the three most interesting unifications that I think Everett contributed to or also inspired are these. So one is the unification of the measuring apparatus and the systems that are to be measured. In this way, we have a nice way of looking at quantum theory as a fully universal description of what's going on in the universe. Also allows us to have a nice unified picture of the other most fundamental theory of physical reality we have, which is general relativity, because quantum dynamics, if regarded in this unitary way, is both local, in the sense it satisfies this very strict notion of no action at a distance, and deterministic. And finally, there is this very nice step, which is the unification of quantum and classical universal models of computation, which isn't something that Everett directly brought about, but I think it's undeniable that one has to take quantum theory seriously in order to think about and understand quantum information and the universal quantum theory machine. And it's on this particular point that I want to focus. That's why it's in red, because there is an element that's missing from the quantum theory of information. And it's something that when we'll find it, when we'll create and find this new, this element that's currently missing, will bring about a further unification. So if you open a textbook on quantum information or any of the nice papers that laid its foundations, most of the theorems that are proven there are fully based on the formalism of quantum theory. So in a way, it's an information theory, but it's really heavily based on the machinery of quantum theory. And this is not satisfactory because the information theoretic concepts are by definition more general than any specific dynamics. And it would be desirable to have a more general way of proving these statements, which only relies on information theoretic aspects and doesn't refer to specific elements of quantum theory's formalism. So what I'm thinking about is something which we might call, for fun, quantum information without quantum theory. And this is what I found very promising in this idea that David Deutsch had, which is kind of called the Constructor Theory program, that he put forward around about the time I was doing my PhD, in order to generalize the quantum theory of computation. And one of the aspects in which the generalization should go is exactly this one. So trying to emancipate the quantum theory of information from specific features of quantum theory's dynamics. Now, what does it have to do with the universality of quantum theory? Well, it has a lot to do with it. And that's what I found really promising in constructor theory itself. So to see why this is interesting, we have to consider a problem. And this problem is best introduced by some kind of example. So the problem arises in this context where one can question the universality of the quantum multiverse when there are some rival theories that might be describing other subsystems of the universe which may not obey quantum theory. So of course, gravity is one of the traditional ones that are being suggested, but there could be others. And so I want to stay general. So Q is this quantum sector of the universe. S is some other sector that may or may not obey quantum theory, and therefore in a way somehow challenges this idea of the fact that the multiverse or quantum theory itself is actually universal. So the question is it possible to have a system of this kind? So where there is a quantum system and there is another system that doesn't obey quantum theory, and somehow they are coexisting and interacting with each other. And of course, the answer to the question depends on how one defines the interaction, and also on what one means by, what we mean by non-quantum. And this is where constructor theory is useful. But before going to that, let's consider one answer to this question that was given a while ago by Bryce DeWitt. So DeWitt had this somewhat humorous way of talking about what he called the totalitarian property of quantum theory. which goes as follows. So the quantization of a given system, Q, implies also the quantization of any other system to which it can be coupled. And so that means the quantum theory, so therefore, so the quantum multiverse and so on, must immediately be extended to all physical systems, including the gravitational field. Of course, he was interested in this problem because he was trying to find arguments to support the program of quantizing gravity. But I'd like to consider this statement of the Wits as a general statement about any system that may or may not obey quantum theory. And in this sense, I think I regard this as a very interesting statement. So it's somehow the Wit was suggesting, and he has a proof of this, that if you have some reasonable assumptions about dynamics of two sectors, one being quantum, the other one being classical, then, and you make them interact, then somehow the classical system has got to pick up some quantum features. Now, this statement has been made in different ways. There are some works by Peres and Terno, and also by Page and Galke, who have suggested ways of bolstering this type of statement, and others. But also it's been questioned. So, you know, Sudarshan collaborators' work, and Holland and Reginato, some of them. I think there are lots of different proposals for interacting classical and quantum fundamental models for dynamics. So now I would like to suggest a way to move forward from this theorem that the Wit proved, and in a way that we can make it stronger. And this will use constructor theory. So one aspect in which the Wit's argument can be improved is that, just like quantum information, as I said before, it assumes many dynamic specific features. So it uses things like Lagrange mechanics and other aspects of the formalism that comes with it. So it would be very desirable to make it more general, to make it stronger and try to relax some of these assumptions. And so we can use, my suggestion is to use constructor theory to do that. So now I'll enter a digression. So I'll talk a little bit about constructor theory, and then I'll go back to showing two possible ways in which we can improve on the Wit's argument. Okay, so constructor theory, you can think of it as a meta theory. So it's something that exists as a sort of deeper level than, say, any particular dynamics. In order to make sense of its statements, you have to assume already to be given a theory with some set of allowed states and a partition into subsystems and other things that I won't list here. But the point is that you don't have to fix a particular dynamics. And then you can define attributes as sets of states. And then the main objects of constructor theory are tasks. And these are, if you like, the generalization of computational tasks. So they are sets of ordered pairs of input-output attributes that specify a physical transformation. And they can be allowed or disallowed in a specific way that I'm going to explain in a moment. And the best way to talk about how a task can be allowed or disallowed is to talk about the constructor, and that's where the theory gets its name. So constructor for a given task can be modeled within a particular dynamical theory as a system that's part of the environment of the system in which you want to perform the task, which can be coupled to this system, bring about the transformations stated by the task, and crucially stays unchanged in its ability to do it again. So for example, in quantum theory, you can think of it as, say, a subspace, which is invariant under some the dynamical laws that you are considering. But it need not be quantum theory, it could be a more general type of dynamics. And the name comes from von Neumann, who thought of this generalization of the quantum Turing machine, which he called the universal constructor. But in this case, constructors are actually much more general entities, and they don't have to be universal. Okay, so why is the concept of the constructor useful? Well, because the key aspect of it, the fact that it stays unchanged in its ability to cause a transformation again, allows one to abstract it away from the description and then only phrase principles or the laws of constructor theory as requirements on whether a constructor is or isn't allowed to be approximated to arbitrarily high accuracy. And so that's how we end up defining what it means for a task to be possible or impossible. So a task is impossible if there's a law of physics that forbids its being performed to arbitrarily high accuracy, and otherwise it's possible. And of course, you can think of many examples of laws that say that some tasks are impossible. For example, statement of no cloning theorem is one way in which you can think of it as forbidding the task of cloning for the case of quantum theories. You can think of the conservation of energy as another such statement, and so on. Now, this is interesting because statements that are formulated with possible and impossible tasks become scale independent and exact. And it's all because you have abstracted away this constructor. And that's the key aspect of constructor theory. And that's why it's interesting. And it allows us to make somehow meta statements about dynamical laws without specifying any particular one, just requiring that they are compatible with the general constructor theoretic principles. Okay, so now I'll specialize to the constructor theory of information, which is a particular kind of application of constructor theory, which will be then useful for our problem of generalizing the Wits argument. Okay, so the constructor theory of information, something I've been working on with David, it's a way of, let's say, achieving two things. One is that it unifies, provides a framework to unify classical and quantum information in a way that it doesn't rely on probabilities, it's exact, and it doesn't rely on quantum and classical dynamics, which is why we're using it in this particular talk. But there's another aspect to it, which is also very interesting, and it's the fact that it's an attempt to provide conjectured physical principles that are necessary for what we informally call information to be embodied in physical systems. So often when we talk about the physical theory, or even about the theory of information as classically conceived, we assume many regularities to be out there in nature in the form of interactions being possible or allowed. And constructor theory of information provides a statement of what some of these regularities are. And they're all in terms of principles that dynamics that can support information should obey. So that you can think of them as a bit like the conservation of energy or the principles of thermodynamics. Okay, so I'll now explain a few of these principles because they are useful for the generalization of the Wits argument. So the first thing we can do with the constructor theory of information is to define a class of physical systems that are capable of instantiating information. And when I say this, people might say, oh, but what do you mean by information? Well, I'm taking information now as an informally defined concept, and I'm now indirectly providing a physical definition for it by conjecturing the regularities that have to be out there in order for information processing to take place. And so the first thing you do is to define this class of systems that we call information media. You can think of these as systems that can contain what is broadly called classical information. So an information medium is a system with a set of disjoint attributes on which you have a set of tasks being possible. So all the permutation tasks and the copy task. now, very simple example, a bit with two attributes 0 and 1. The permutation tasks are these, and the copy task is this one down here. So therefore, you can think of it as a generalization of a control knot. And so a system with these properties is called an information medium, and the set X is called an information variable. So it's a set of attributes that can be permuted in all possible ways and copied. Then there is this principle that we conjectured, which is called the interoperability principle for information. And this says that if you have two information media, each of which satisfies this definition, you put them together, no matter what the dynamics, specific dynamics is, they've got to satisfy this requirement that when you consider the joint system, it itself is still an information medium with an information variable that's a Cartesian product of the two separate information variables. And so if you figure out what this means in terms of permutations at the level of the global system, this basically implies that information variables must be copyable from any information medium to any other information medium that has at least the same capacity. And so this is a conjectured law of nature, if you like, and this will be used later for the proof of the generalized Wits argument. Now, David and I also added a constraint on information media. So you can think of a restricted class of information media that we call super information media. And these are systems that should provide a generalization of quantum systems, of systems that can support, at least qualitatively, all of the features of quantum information processing. And specifically an information, so a super information medium is an information medium with at least two information variables, say X and Y, whose union isn't an information variable. And again, just an example to understand what I'm talking about. A qubit qualifies as a super information medium with two variables corresponding to two different bases, because when you take the union of those two sets, X and Y, for example, you can't copy the resulting set. And so that's one example, but the idea is that this is more general, is not using any of quantum theory's specific features to talk about this, this particular class of media. And finally, you can prove that there is this kind of structure between information media, super information media, and quantum systems. So super information media have all the qualitative properties of quantum systems, which is why quantum systems are like a sub-element of this super information media set. And information media are this more general set here. And note that this can be proven exactly, so we're not using probabilistic schemes or approximations of sorts. And this is quite nice because it gives us a framework where we can basically talk about generalized quantum systems in this nice exact way. And also, I later proved that there is a subset of super information media obeying some additional constraints for which you can construct probabilities in much the same way as you can for quantum theory with decision theory type argument, which is also nice because then we have a quantitative handle on certain phenomena, chiefly things like entanglement. So in this framework, you can define qualitatively, and we are hoping quantitatively also, most of the quantum information features of quantum systems, which is very nice. And it's very nice because it can help us with our task, the task that I set to myself at the start of the talk, which was to generalize the Wits argument. So let's go back to that. We need an additional small step, which is that we need to talk about the notion of non-classicality within this new super information framework. And non-classicality is a slightly lesser feature than being, than super information. And it's the property that the system has at least two variables, X and Z, so two sets of non-overlapping attributes, which is also disjoint from one another, with the property that it is impossible to copy them jointly to arbitrarily high accuracy. And this generalizes the familiar notion of the fact that X and Z don't commute. It's just that it does in this operational way that doesn't use an explicit formalism to state the condition for being non-classical. And as I said, this is a lesser property than being even quantum, because, for instance, if Z is an information variable, something that can be measured, X may not be. It also could be that X isn't fully permutable, and so on. Okay, now we've got all the ingredients. We can go back to the task, and the task was, to provide this generalized information-theoretic argument for what the Witt called the totalitarian property of quantum theory. This is some work that I did with Vlatko Vedrol, out also of the fact that I think Vlatko was largely concerned or dissatisfied with the fact that some of these properties, these general principles that we had in constructor theory, didn't have a connection with immediately testable things. And I think this work is bridging the gap between these principles that are very general and abstract and something that could actually be tested. So we assume three general principles now. Locality. I won't say more about locality. It's a stronger property than no signaling. And I think Paul Raymond Robichaud will later talk about it in all the details. Interoperability of information, which I defined earlier. And then there is this third requirement, which is not quite right what I wrote there, because it's a more involved type of requirement, but for the purpose of this talk, it's something that requires the subsidiary theories of constructor theory, the dynamics that obey constructor theory to be one-to-one, so logically reversible. And so with these assumptions, we can prove a nice theorem. And the theorem says that if it's possible to couple a superinformation medium Q with an information medium S through a copy-like interaction, then S must be non-classical. And so this is the attempted generalization of the Witts statement in a way that doesn't rely on specific dynamical laws. And now there is a further step that we can take, which is interesting. So we can ask, is it possible to drop one of these three assumptions in order to prove this totalitarian property of superinformation or quantum theory, quantum theory? And we can do that by adding, instead of having just one superinformation medium, having two of them. So you can use two superinformation media, which I call here Q and Q prime, and formulate a statement of this kind, which says, assume locality and assume the interoperability of information. If the system S that you're trying to show has to be quantum can mediate locally entanglement between these two superinformation media, so Q and Q prime, then S must be non-classical in the sense that I said earlier. And when I say entanglement, I don't mean entanglement defined within quantum theory. I mean it can be defined at least at the qualitative level within this superinformation framework. So we are still dynamics independent when we formulate this theorem and when we prove it. So that's the second version of how to generalize the Witts argument for the totalitarian property of quantum theory. And I find this very interesting. I'd like to hear what you think about it, but I think the reasons why I find this interesting is that, so these principles that underlie the theorems are nicely expressed in terms of statements that are not dependent on specific dynamics and they're independent of the scale, which is in general a feature of constructor theory. And the other thing is that the second theorem that I mentioned suggests actually a class of experiments which one can perform in order to check, in order to provide a witness of whether an unknown system S is or isn't quantum, or in fact, I would say is or isn't classical. In the sense that if this mediator S can act as a channel to create entanglement between these two other systems, then we can conclude that S is actually non-classical. So all classical models for S should be discarded, provided that they satisfy these two axioms of locality and interoperability of information. And this is nice because it ties in with some recent experiments that were proposed, a bit along the line of also what Page and collaborators had proposed quite a while ago, to test quantum effects in gravity through probing it with two quantum masses. But the reason why I find this interesting is mostly this more general theoretical reason that I regard these results as a first step towards providing a host of generalizations of these results that we have in quantum information theory without having to assume the specific features of quantum theory. And so in a way, this is a bit like a generalization of Bell's theorem, if you like. So in the case of, or at least it has the same logic, let's say. In the case of Bell's theorem, you can rule out a host of models for certain systems that display certain kinds of correlations that violate given inequalities. In this case, it's very nice that under some axioms, just like in the case of Bell's theorem, you can rule out a host of models that are classical for this system S. So I think I am almost at the end of the talk, in the sense that I'll leave this, the ending point is a question. So does this result and others that we have hint at the fact that we might be able to provide a theory of the quantum multiverse, which actually goes beyond quantum theory itself, its formalism and so on? And then if that's the case, what are the features that we, of the formalism of quantum theory, and that we might be happy to part with? And, I have some thoughts. For example, could it be the equivalence between the Schrödinger and the Heisenberg picture? Perhaps we should question more things like the superposition principle. And I think some of the talks that will come today, or perhaps in the next few days, will kind of discuss a little bit these things. But mostly this question is for you, in a way that, I think this kind of audience understands quantum theory in a very deep way, and it would be nice to hear your thoughts. And so on this note, I think I'll just stop the talk, and I'm very happy to have a conversation and answer questions. Thank you for listening.
Thank you, Chiara. Thank you very much. I would, if everyone wants to join me for clapping, please go ahead. Great. Thank you. So we have plenty of time for questions. There is one hand that is raised by Professor Don Page. Don Page, if you would like to unmute yourself. And yeah.
Yeah. Hi, I was trying to think what an example of this, although when you talked about something other than quantum theory, I don't know. I don't think it satisfies a lot of the axioms you propose later, but it occurred to me that consciousness might be something, because I mean, it seems like you can't, as far as I can see, there's no way to logically deduce consciousness from quantum theory or from the quantum state. You need something, you need something else. So it may be, the simplest view seems to me that it supervenes on the quantum state. That for example, I propose that the measure for conscious perceptions is given by the expectation values of certain operators, but then the state in the Heisenberg picture doesn't change at all in this simplest version. But Andre Linde has proposed that maybe consciousness could even have an effect back on the state. But I don't know. I don't know about the these tasks you talked about, I'm not quite sure consciousness could do that sort of thing. But I mean, it does seem to be something that isn't explicitly quantum. Although certainly there must be a physical parallelism relating it to that. But in some sense, it's different from the quantum theory. And I wondered whether anything that you worked on might apply to that.
Well, I think in regard to consciousness, we are somehow, in a way, we're very far from having an exact theory of it within physics, and it's even questionable whether that's that's possible at all. However, because I think I'd like to think that whatever we are doing with the brain is actually some kind of computation. So I'd hope that some of these principles that I mentioned, for example, this interoperability principle and so on, should also underlie whatever is the particular program that we are running when we think. Now, whether that is going to violate the laws of quantum theory or not is, I think, is an open question. I don't have any reason to expect that that's the case, but who knows, maybe it is. And if that's the case, then hopefully these principles, because they're more robust than quantum theory itself, should survive and should still be valid. But I don't know if this answers your question. I don't think we have thought specifically about consciousness in this work. And also I should say that in general, I think we have a very poor understanding, we've got like a descriptive understanding of consciousness and some theories that say why it's compatible with underlying dynamical laws and so on. But I don't think we have an explanatory theory for it yet, other than maybe at this higher level. So I don't know, I can only speculate about some of these things. And in fact, I'm interested to know whether, you people have different views.
One crazy idea I had, I don't think it's very plausible, but if it were true, it would be extremely exciting. And that is, it seems to me that our consciousness depends on something non-local in the brain. If it was completely local, just localized to a point, you'd only have a few fields or something that could read. It's surely when we're conscious of something, it depends on some region spread over the brain. Now, in the view I think is most plausible, that it's an epiphenomenon, then the expectation values of some operators maybe give this consciousness, but they don't act at all on the quantum state. But if you raise the possibility that these non-local operators acted on the quantum state, contributed to the Hamiltonian, there conceivably could be non-local communication or non-local signals sent across whatever region, has these consciousness. So I don't put this out as something I think is very plausible, but it does occur to me, and that maybe the one chance in a million that it might be, well, I don't know, I'd even give it that high a probability, but one chance of a million that it might be right. It would be extremely exciting if we could see that there's non-local propagation of information inside of conscious beings, although it raises all sorts of ethical questions of how you test that.
Yeah, I mean, the somehow slightly bad news is that if things are non-local, then the theory of information we have doesn't apply. So we might have to rethink about, for making sense of the model you have, we might have to rethink about things like even just what it means to independently prepare a subsystem, measure it, and so on. So all of these notions I mentioned are based on locality, and it's a strong locality property. Like, as I said, I think, let's say like the locality property is satisfied by quantum field theory at the level of Q-numbered operators. But yeah, I'm as I said, I mean, this is not specifically what this theorem should be useful for, but yeah, maybe we can discuss a bit more about these specific models you have. I'm not. This is not the center of my thinking.
I'm also curious because it seems like quantum gravity is non-local in the sense that there's the constraint equations that the energy of the system is recorded by the gravitational field all the way at infinity. And so if you have an energy eigenstate, say if it's asymptotically flat or something, if you have an energy eigenstate, there's no way to change there's no way that you could make a change in the quantum state inside without changing it all the way out at infinity. So I don't think this permits propagating signals fast in light, but I mean, I think it does mean it's impossible. Even if suppose God just said, I'm going to keep general relativity and so on, he could not change the state in the middle of the system without changing it all the way out to infinity because of the constraint equation. So I'm curious, because it seems like quantum gravity is not local.
Well, I think so perhaps non-locality, unfortunately, is a very loaded word. The way I think about it is dynamical and somewhat counterfactual. So it's about the fact that if you were to change so if you've got like two space, like separated subsystems, and you were to interact with only one of them, the other shouldn't change. And to think about this, you would have to change the constraints. You would have to set up a dynamically evolving situation where you're considering what happens if you were to do this and that. So in that sense, I think it's compatible with the kind of quantum gravity models you were referring to. But of course, I'm happy if quantum gravity experts are around if they want to say something about it. But I think the locality I'm talking about is compatible with what you are referring to.
Well, it's certainly a very approximate locality, and that's kind of the mystery of some of the things, the firewall arguments that they, if you assume precise locality, you get into these paradoxes. But if quantum gravity theory is really not completely local, then you can ameliorate the information loss problem for black holes.
Well, that is also okay. That opens like another very broad direction for discussion, in the sense that is also questionable whether there's a paradox or. So I think well, I mean, yeah, I guess some of the derivations that are behind that claim are perhaps not taking. Yeah, I think I quite like your take on that work. On the information loss paradox, but I think the derivation we have of it are themselves not fully consistent with unitary quantum theory, and then perhaps the paradox is just the fact that, as you I think suggested, there's some defect in the way the paradox is derived. Yeah, so
if you want, guys, we can perhaps pursue this discussion. We have a discussion period and we have breaks. If you want to, it would be good to have at least one more questions. There was a question in the chat by Scott Aronson. I see he's put in his camera. So perhaps, Scott, you want to ask it yourself?
Sure. Yeah. So, I mean, I think, one of the most basic questions that you can ask about any abstract framework is, do you get out of it more than what you put in, right? And so I want to understand better. So I was wondering, if you could say something about like the proofs of your theorems of the necessity of totalitarianism. Like, is there an interesting trick beyond just sort of clearly spelling out, what are the axioms of constructor theory and what do they say and so forth?
Sorry. Well, the trick is, I would say so the two tricks are this locality property. So that's very strong, that requiring that when you have, so it's actually locality plus realism. So I think, again, I'm entering the topic of a talk that will be given later. So the fact that, for example, with qubits, if you look at them, the way they behave in the Eisenberg picture, and you make them interact with each other, later on, the descriptors of each qubit depends on the descriptors of the other qubit at an earlier time in the case of a general interaction. And there's nothing else that can specify the descriptor of a system at a later time as a function of the descriptors of systems at earlier times. That's one very strong requirement, which happens to be true of the theories we know, but that could be questioned. And the other one is the interoperability principle, because it kind of requires all of these copy-like interactions to be allowed between subsystems. That's quite strong. Although I have to say, physically, from the physics point of view, I think it's nicely plausible in the sense that it's a reasonable requirement for theories to be testable and so on. So the nice thing about the theorem is, I think, the fact that these axioms are physically well motivated and they are general. So I think the appealing aspect is that you don't have to specify a specific formalism to derive it beyond the various properties that you require of theories to be expressed in terms of tasks. But yeah, I agree with you. The axioms are, in a way, they are the explanation for why you get the result. I absolutely agree with you. And in that sense, I regard them as maybe nicely explanatory of how come we expect this totalitarian property to be true. Yeah, it's a nice question. Thanks.
Yeah. All right, thank you.
Great. I see Lev had a question. Please, Lev, go ahead.
Thank you, Chiara. I think it was very interesting. But first, a comment. I don't think, at least in my understanding, this is not the spirit of Everett. Everett wanted to believe that quantum mechanics is the end of story. It's you are not supposed to go anything further. This is the quantum mechanics explain everything, and what it doesn't look like, we have to find a quantum mechanical explanation. But my question is that this approach is very strongly relies on the concept of information. Mm-hmm. I understand it's important. I have to know how to send messages, that how you can manipulate and whatever. It's less clear for me that this is the basis of understanding the universe. And you said very little. You said that everyone can understand whatever he wants about information. I think you should give much more motivation and explanation why information is important to understanding the universe.
Okay, okay, the first point is easy to address in the sense that we are standing on the shoulders of Everett. So I was kind of trying to do kind of along the lines of what the title of the conference is suggesting. I was certainly going beyond whatever he was suggesting in his thesis. And as I said, I was inspired by this interest for unifying things further. Okay, so about information, it's a very long answer that I should give, but I think in short, there is, so what we're trying to do with this stuff isn't to take information as fundamental and then build a theory of the universe on information. That isn't what we would like to do. What this is supposed to do is to, just like thermodynamics did for things like energy and heat, for instance, although that was done in a scale-dependent way, but for the moment, forget about that. So just like thermodynamics did that thing for energy, we'd like to have a theory of what it means for the stuff that we informally call information to be embodied in physical systems. So what are the microscopic fundamental regularities that you must have in physical constituents of the universe for it to permit things like computers and information processing entities, more generally speaking. Now you could say, well, maybe that's not so interesting. I mean, I don't care what computers do. So if that's your view, I can't argue with that. But I have the opposite view. I think the physics of computation has led to very deep, seems to me, realizations about quantum theory, for example. And the hope is that somehow by studying the information-theoretic structure of quantum theory, you could actually get at a deeper symmetry of it, which is the one that's robust and will stay should quantum theory be modified one day or another. And I know, Lev, that you don't like to think of dropping quantum theory, but this is, let's say, an attempt to keep all of the nice things of quantum theory, unitary quantum theory, Everettian quantum theory, call it the way you like, even if even in the case where we have to actually modify its formalism. I don't know if this helps, but if not, we can maybe discuss it in a long discussion, maybe. Later.
Thank you. I got the flavor.
Okay.
This is a perfect point to finish officially the session of Chiara. So let us thanks again, Chiara, for your beautiful talk. If you want, and we can stop the recording.